In the previous lessons, we talked about measurements. And measurement is basically a quantitative data using a measuring instrument. However, not all instruments are the same. Some scale can be worth thousands of dollars, but then we have the kitchen scale that's worth $19 from Costco. And here is the reason behind it. It's all about precision. And most important, it's about significant figures or digits. Basically, the significant figures of a number or of a measurement, it determines or it indicates how precise that instrument is going to be. The more precise the instrument, the more expensive it's going to be. So in this video, we are going to look at how do we determine the number of significant figures or digits. So you either use the word digits or figures. They mean the same thing in terms of number. First of all, if we look at the structure of a number is made up of one or more digits. Okay? So what do I mean by that? If we look at number 1, that number 1 is made up of the digit 1. But if I add another 0, now number 10 is made up of the digit 1 and the digit of 0. If I add a 5 here, I have 105. This number is made of 3 digits. So keep that in mind, how digits and number are different. Now let's talk about significant figures of a measurement. The first thing is that the number of the significant digits in a number or in a measurement shows the measurement precision. A measurement number with more decimal places will be more precise. That means that instrument that is used to determine that measurement is more expensive in most cases. Now, the term precision is not the same thing as accuracy. Accuracy is how close are you to the accepted values. How close are you to the accepted literature values, okay? Where precision is about the instrument that you are using. And that is, you can still get inaccurate measurement even when you are using a very precise instrument because you are using the instrument incorrectly. If you use it incorrectly, therefore the data will be inaccurate. So keep that in mind. Now let's talk about the rules that we use to determine if a digit or a figure is significant or not. Now, what does the term significant mean? When we look at the term significant, this word significant indicates that we can prove it. That is, we can prove using the instrument, we can actually point out, hey, right here represents this specific digit. And the beauty behind measurement is that all measurement, of course, is a number that consists of digits. But if we look at all the digits, the last digit is the most important of all, is that this digit is always estimated, either by us or by the measuring instrument software itself. So again, the last digit is always estimated. And going back to the term significant, when a digit is significant, it is proven. For example, this digit right here, it is proven. It is significant. Where this here is estimated, but it is somewhat significant. That's why I said the last digit is always estimated. So this is the last significant digit that you will see in the measurement. So the last digit of a measurement is also the last significant digit. So that's the term significant. Now let's talk about the rules to determine if a digit is significant or not. There are only 3 situations or 3 rules when a digit in a measurement number is significant. If a digit does not apply, I said does not apply to one of the 3 rules down here, that digit will not be significant. So it must apply to one of the 3 rules right here. The first rule is all non-zero digits are significant. 1, 2, 3, all the way through 9, they are non-zero. And what are 0? Of course, that is a 0. Then now we're going to talk about the 0. The 0 are the tricky part of this rule. There are two situations. When a 0 is in between two non-zero, it is significant. So that 0 is significant. But here is rule number 3. This is where it gets tricky. A 0 in a decimal number, so again, it has to be a decimal number, and it is to the right of a non-zero. This two condition for number 3, the two condition here must be met, or else it would not be significant. Let's look at specific example. Here I have 1600. These two are significant because they are non-zero. But look at this 20. First of all, they are after a non-zero. But is this a decimal number? No. Therefore, this 0 are not significant. So how many sig fig do we have? We only have 2 sig fig. And SF is the abbreviation for significant figures. Let's look at another example. We have 16.00. Of course, the 16 is significant. But look at this 0. Is it significant? First of all, it is a decimal number. That's good. Now, is it to the right of a non-zero? Yes. So therefore, this 0 are significant as well. So we have 4 SF right there are significant figures. Now, let's look at 0.001. First of all, we know the 1 is significant. But look at this 30. All the 30 are in a decimal. That's good. What about part 2 of rule number 3? Is it to the right of a non-zero? No. So therefore, it is not. So this measurement only has one significant figure. Then we have 0.001000. Look at this 30 here. They are in a decimal number, but are they right after a non-zero? No. Bam. So they are not significant. Then we look at the 30 after the 1. First of all, they are in a decimal number, and it is to the right of a non-zero. Therefore, 1, 2, 3, 4. Now, there are exceptions to this rule. The first exception is this. Significant figures are only applied to measurement. That is, we're using an instrument to determine the quantitative data. So if a number is not measured, we do not care about the significant figures of that number. That is, we can ignore it, or we can assume that it has infinite significant figures. For example, counting numbers such as 5 apples, 100 pennies, and 100 tablets. These number has infinite number of significant figures. That is, we can ignore it in our calculation. Let's talk about the next exception. That is the coefficient part, more specifically, the decimal part. Because the term coefficient is too specific about the scientific notation number. Because again, the coefficient must be greater than 1 or equal to 1, but less than 10. Sometimes that part we call it the decimal part because it does not meet the requirement. So we can have a number like this, 11.1 times 10 to the power of 2. This is the decimal part because it's not purely coefficient part for the scientific notation. But let's go back to this. The coefficient part, or specifically the decimal part, is the only part that determines the number of significant figures. So that is, we don't care about the exponent when we determine the significant figure. In this case, we have 1, 2, 3. So we have 3 significant figures. Let's try some more example. I have this number right here. This decimal part is the only thing that we care about. We can ignore 10 to the second power. So in this case, this is a non-zero, so significant. And these 0 are significant because look at rule 2. They are in between 2 non-zero. And then we have the 7 that is significant. Then we have a decimal number. Then we have a 5 that is a non-zero. What about this 0? This 0 is in rule number 3. It is in a decimal number, yes. And it is to the right of a non-zero, so therefore it is significant. So we have 2, 4, 6 significant figures. Let's try the next one. We have 0.007300 times 10 to the negative 3 moles of water. So we can ignore the exponent part again. We just cover that. Let's look at this. Are these zeros significant? No, because look at the rule number 3. It is not to the right of a non-zero. It is in a decimal place, but it's not to the right, so it's not. So as well as this 2, 0. 7 is significant. What about 3? Yes, because it's a non-zero. What about this 2, 0? Of course, yes. It is in a decimal number, and it is to the right of a non-zero. So 1, 2. They are both significant. So the total of 4 significant figures. Let's do some more example. We have 10500 grams of NaCl. 10,500 grams of NaCl. In this case, the 1 is significant because of non-zero. This 0 is significant because it's in between two non-zero. This 5 is significant because of the non-zero. And this 2, 0 are not significant because they are to the right of a non-zero, but they are not in a decimal number. So we have 3 SF, or 3 significant figures. Then we look at this number right here. These 3 0 here are not significant because they are in a decimal number, but they are not to the right of a non-zero. So they are not significant. And of course, the 1 is significant. This 0 is in between two non-zeros, so it is. And this 0 is in a decimal and is to the right of a non-zero, so they are significant. So we have 4 SF. Then here we have a scientific notation number with the coefficient not being valid. But again, we just ignore the exponent and we look at this. This 7 is a non-zero, so it's significant. This 0 is in between two non-zero, so significant. These 2, 0 right here are not significant because they are to the right of a non-zero, but they are not in a decimal number. So we have 3 significant in this case. Then down here we have 105 or 105 milliliter of HCl. First of all, this 1 is significant because of a non-zero. This 0 is significant because between two non-zero, because a 5 is a non-zero. Then this 2, 0, are they significant? Yes, because it is in a decimal number and it is to the right of a non-zero. So we have 5 SF here. Then the last example, we have 50 drops of H2O. They're supposed to be H2O. And 50, first of all, if we look at just 50, not looking at the drop of water, the 5 is significant figures, but a 0 is not. So we can say it's 1 SF. But now if we look at the whole entire thing with the word drops, we don't have an instrument that measures drop. We have to count 1 drop at a time. So this is a counting number. It's not a measure number. So therefore it has infinite sig fig. So that's wrong. This is the right answer.